Next, I want to prove some properties of Laplace transforms, and I'll do one that we used already and one that we didn't use, and actually I'll show how these are useful for calculating more Laplace transforms as well. So let's calculate the Laplace transform of the derivative of a function, given that we know the Laplace transform of the function. And this is going to turn into that long, ugly formula for the Laplace transform of the nth derivative of the function, eventually. So let's just use the definition of Laplace transform to do this. So integral from 0 to infinity e to the negative st, and then we're just going to take whatever's in here, put it here, dt. Okay, and then we need to do integration by parts to get rid of the derivative. So we need to pick u equals e to the minus st dv equals f prime of t dt, and that way we'll be able to get v equals f of t, and then du is negative s e to the minus st dt. Okay, then we have a uv, so e to the minus st f of t, and then minus v integral of v du. There's a minus sign here, so this is actually plus. S is a constant, which we'll pull out in front, and then the integral, sorry, this goes from 0 to infinity. We have a definite integral now. Integral from 0 to infinity, e to the minus st f of t dt. Okay, we recognize this as the Laplace transform of f of t, so that's good. We'll be able to get that. Over here, so we need s to be 0 for the improper integral to be defined, otherwise it diverges. And when s is greater than 0, then this part, as t goes to infinity, goes to 0. So we have 0 minus, and then we put in 0 for t, we get f of 0. And then we have plus s, and then this, as we said, was the Laplace transform of f of t. So there we go. There is the original incarnation of this formula, where n equals 1, the first derivative. Laplace transform of the first derivative is s times Laplace transform of the function minus f of 0. If we wanted to get higher derivatives, we can. Let's just do one, Laplace transform of the second derivative. We're going to use this formula, but put in f prime for f, basically. Because if we put in f prime for f, then the derivative of that is f double prime. So we're just writing f prime everywhere we see an f. And then we can use the formula again. For this, we can plug in what's written up there, s times Laplace transform of f of t, minus f of 0, regular bracket, complicated. Okay, so that is Laplace transform of f prime of t, and then we still have this minus f prime of 0 out here. And then we can expand this. This is s squared Laplace transform of f of t minus s times f of 0 s times f of 0 minus s to the 0, which is 1 times f prime of 0. So we see the formula emerging, and then here's a reminder. This is what you would do if you did that n times. We get s to the n out here. Here this was s squared, and it was the second derivative. Laplace transform of f of t minus, and then the powers of s decrease, s to the n minus 1, and we start getting f of 0s minus s to the n minus 2, f prime of 0 minus, and so on. And then we end with the term before this is s times f. These need to, the number on the derivative and this number need to add up to n minus 1. So this is 1, so this is the n minus 2th derivative minus s to the 0, and then we have the n minus 1th derivative at 0. And we can get that whole formula by repeatedly using this formula that we just derived. Okay, what is that good for? Well, last time we found the Laplace transform of sine of bt, which was b over s squared plus b squared. We calculated that from the definition of Laplace transform. If we wanted to do the Laplace transform of cosine of bt, we could also do it from the definition. But remember, it was pretty ugly. We had an ugly integration by parts. So let's try to avoid that if we can. I'm going to write this as Laplace transforms are linear, so if I put a constant out here, I can multiply, basically I'm multiplying by b and 1 over b, but I can pull the 1 over b out here. And then, what is this? This is just the derivative of sine bt. Okay, so I can use this formula. This is now, I leave the 1 over b out here. I have an s Laplace transform of sine bt minus sine bt at 0, which is 0. Okay, so what is this? This is 1 over b times s times Laplace transform of sine bt, we know, b over s squared plus b squared minus 0, so there's nothing there. So these b's cancel, and we end up with s over s squared plus b squared. And if you checked the table, you would see this. So if you're ever without a table, you can derive these. It takes a little bit of time, but we can do it. Okay, we're actually going to do another property that we didn't do last time, and it'll help us calculate more Laplace transforms. So this is the property Laplace transform of t times f of t, given that we know the Laplace transform of f of t. Okay, so we're going to write down the definition again. So e to the minus st t times f of t dt. And we're going to do a super sneaky trick. Let's just write this over here. So the derivative with respect to s, maybe we should technically write partial derivative if you know what that is, but that's okay. So basically we're holding t constant and we're finding this derivative. Well, if we hold t constant, then f of t is constant actually. So we can take that out as constant, and then we just need to derive e to the negative st with respect to s. So we pull down a constant of negative t actually, e to the negative st. Take a minute, make sure you agree with that. T is a constant, so the derivative of this with respect to s is this. That looks really similar to what we have here, except for the negative sign. Right, so I can multiply by a negative sign and get that. So I have a negative d by ds f of t e to the negative st. And then integral with respect to t. So that's weird, we've got s's and t's going on. Super fancy trick there. Probably very difficult to think of the first time. And now, as long as our functions are nice, nice being every function that you see in this class is nice, so don't worry about it, we can switch the order of integration and differentiation. And we can also pull out a negative sign in front. So this step is for nice functions. Remember I said the easiest version of nice was continuous. You need a little bit more than that here. You need it to be probably at least continuously differentiable, maybe more than that. But we'll leave it at nice. We won't worry too much about exactly what we need. Okay, we're left with an f of t e to the minus st dt in here. Oh, but wait, this is the Laplace transform of f of t. So we have negative d by ds Laplace transform of f of t. Weird. Okay, what does that mean? How do we apply that? Well, this actually allows us to calculate the Laplace transform of t, which we could do with the definition. We would need an integration by parts, but maybe we're tired of doing that, so let's make as few integration by parts as possible. T we can think of as t times 1, so f of t is going to be 1, and then we're just going to use this formula. So this is negative d by ds Laplace transform of 1, which is 1 over s. We calculated that last time, or you can look it up in the table. And then this is negative derivative of 1 over s. We pull out a negative, we decrease the power by 1, so it's a power of negative 2 now, so 1 over s squared. So these properties not only allow us to solve differential equations, it can also help us calculate more Laplace transforms, which is good.